My name is Grégoire Petit, and I'm here today to present to you the paper that I wrote with Michaël Soumm, Eva Feillet, Adrian Popescu, Bertrand Delezoide, David Picard, and Céline Hudelot about Exemplar-Free Class-Incremental Learning and the different ways you can pre-train your network to make it better. So I'll divide my presentation into three parts. The first one will be an introduction and explaining to you the interest of class-incremental learning, especially in the exemplar-free setup. Then I will describe the study that we set up, and finally conclude with some takeaways and some perspectives. So, firstly, I'd like to go back to the definition of learning. If we go into the dictionary, to learn is defined as to gain knowledge or skill by studying, from experience, being taught, etc., etc. Therefore, learning is a process that is continuous and incremental. So the first question that we can ask ourselves is, why can't we just retrain the model from scratch like we do in classical machine learning? The first reason is because of memory constraint. Then you also have computational constraints that are taking place. Finally, the number of states that we want to include in our model is also a great challenge. And finally, the variability of data streams is playing a lot, including the scenario variability. So now I'd like to present to you the continual learning setup. So let's divide our dataset into n subset of disjoint classes, and we will call this subset states. So we train our model on the first state, and then we test it on the same state on a different subset, but the same state, same classes. Then we go to the second state, we train it, and then we test it on the first and the second state. We go on until arriving to this state n, we train it, and then we test with all the states from the beginning, and so on and so on. So we have now to find a way to evaluate our model. So we know the commonly used metric, which is the accuracy. So it corresponds to the proportion of classes that are accurately predicted by the network. And in continual learning, we can define 4 other different metrics that will be relevant in our studies. And the first one would be the average incremental accuracy, defined as the average accuracies across all the states. Then you also have the first accuracy, which corresponds to the accuracy of the model on the first state. It will be useful as a proxy. We also have the accuracy at the final state. It corresponds to the accuracy of the model upon all the datasets. And another metric that will be interesting in our study is the forgetting. The forgetting is defined as the proportion of the forgetting that happen in the network. So let's say we take a class, we learn it, we compute the accuracy, and we compute the accuracy at the end. We then calculate the first minus the second, and then we have an idea of how much the network has forget. So now we face some specific challenges with the exemplar-free setup. The first challenge is that we are very constrained in terms of resources. We want to embed our network, and then we cannot store everything that we would like. The second challenge that is specific to exemplar-free setup is the privacy and security. For example, if we are dealing with healthcare data, we cannot store patients' data because of specific rules, and then we won't be able to learn, and that's a problem. And finally, there is also issues with timeliness, because as we want to update our model state after state, if we store data, then it will cause some issues. So now that I explained the setup, it's time to explain more about the data that we will use. So in our study, we took some datasets that are very different from one to another. The first is about traffic sign. Then we also have a subset of ImageNet. and a lot of other datasets. For large-scale dataset, we took a specific dataset such as CASIA, which are faces. We took also a landmarks and iNaturalist that are relevant. Now let's delve into the details of the study. So our objective and purpose was to identify and quantify the primary factors that influence the performance of FSIL algorithms. So I'd like to illustrate the statistical study. We have our dataset that we previously introduced. We use two different scenarios that are most commonly used in FSIL setups. The first scenario is when you have half of the classes in the first state, and the second one is with all the states equally distributed. We update our model using 3 different FSIL algorithms, and we have 13 different initial training in order to embed to the rest of the method. It makes a total of a lot of logs, and we want to study for a given metric which of these factors is mostly influencing. So for that, we craft this statistical study in order to provide some recommendations. So let's delve into the details. We took 2 different neural architectures. So the first one is a convolutional network, a ResNet 50, and the second one is a transformer. We initialized our method with different training, such as cross-entropy, BIAL, MoCoV3, DEIT, and DynoV2. We fine-tune on initial classes in some cases not. In some cases, we use an external dataset, otherwise not. And we supervised it using self-supervised learning and supervised learning. So we used 3 different FSIL algorithms, and for each of this configuration, we wrote the amount of time that this particular configuration work, and also the mean accuracy that we get. We can see that DynoV2 is very performing, but also if we fine-tune on the initial state, we lose the interest of the pre-trained model. However, fixed representation methods are very performant with good initial trainings, and overall, self-supervised learning seems to be a good choice. However, we cannot generalize the result by looking at the mean accuracy because we need to analyze the results in a more fine-grained way. So to do that, we performed an OLS regression to fit a model of the following form. So the first step of this regression would be the variable selection. We can see that there are 4 main variables that comes into our study. Let's fit it with an ANOVA, an analysis of variance. We can see that the initial accuracy is one of the most variable for both metrics, and we have to check about the correlations. In our table, we see that there is a big correlation between the first accuracy and the forgetting, and the first accuracy and the average incremental accuracy. And so that's why we will try to get rid of it. So we performed the ANOVA on the 3 remaining variables, and we can see that the initial training strategy significantly affects average incremental accuracy, whereas the choice of the class-incremental algorithm is crucial for preventing forgetting. We also can see that the domain gap between the initial training and the incremental data is a key factor for both metrics. Here is the interaction plot of the best strategies. We can see that for a large-scale dataset, there is different way to pre-train that work the best. For example, a supervised learning approach would work best on something that is correlated to faces. So it's time to recap. So our objective was to identify and quantify the primary factors that influence the performance of FSIL algorithms, and our key finding is that the initial training strategy significantly affects the average incremental accuracy, and that the choice of the algorithm is crucial for preventing forgetting. However, the domain gap between the initial training and the incremental data is a key factor for both metrics. What's next? We have seen that we could improve the feature generalization. Also, we can try to scale up this study in order to study the impact of the scale of the dataset on the performance of the method. So thank you for your attention. I would be happy to answer your questions, and we will meet also at the poster session. Thank you.